Good morning. Okay. Morning. Nice to see you.
Yeah.
So
let
please,
me share
the stage
screen.
is yours.
Thank you very much. Okay. Can you see my slides?
Yes, we can. Yes.
Okay. So then I will start. Yeah. First, let me thank the Roman and the organizers for the kind invitation to present my work in this workshop, and in particular in this session about the QCD critical point, where I'm going to show some of the results that I did in collaboration with Eduard Shuriak at Stony Brook University and myself, Juan Torres. So now in the previous talk already, Xiaofeng just discussed the QCD critical point and the QCD phase diagram in general. And then I saw you here again with some of the experiments, ongoing and future experiments, which are trying to observe some signatures of the first order phase transition and also the possible critical point. So the comment I want to make here is that this hypothetical critical point is located in the baryon-rich region at finite net baryon density in this phase diagram. And in particular, we know from lattice QCD that this possible critical point is favored for a biochemical potential of 2 or even 3 times larger than the critical temperature, and also some theoretical work but based on Dyson-Swinger equations and functional normalization group, as we have seen in talks in this workshop. It favors a critical point at 4 or even 5 times the critical temperature. So it's really in this area here where nucleon physics is irrelevant. In fact, this has been used in experiments to try to measure some net proton observables. And in this case, Xiaofeng also showed this result from STAR about the kurtosis of net proton distribution, where you compute different cumulants of the net proton distribution and then do this ratio, 4th order cumulant, 2nd order cumulant, and to get something called scale kurtosis. And this is the result for the latest result from STAR data, where this kurtosis as a function of collision energy presents this kind of non-monotonous behavior. And this increase at low energies might be some indication of the presence of the critical point. So in this case, proton-proton interaction should be important. And in fact, this kind of observables in net proton distribution should contain some information about interactions among protons. So what is about the interaction about 2 nucleons in general, or 2 protons in particular? Well, usually we can modelize this with the boson exchange model, where 2 protons, in this case, can exchange different excitations, like a pion-like sigma excitation with different quantum numbers. And then in this way, you can describe with some, in a model way, the interaction between two of these nucleons. Now, for the situations we are interested, we have temperatures which are not 0. They are temperatures which are of the same order of the vacuum masses of these states. So you expect for these states in particular, and also the nucleon-nucleon interaction itself, some medium modifications. So in particular, the question I would like to ask here is what could be the main effect, the main medium modification of this nucleon-nucleon potential due to the presence of a critical point. So, well, one has to go to the theory of critical dynamics, and we know that there is a mode, a sigma mode, which is described in general by some effective potential, which you can expand in powers close to the critical point. And the main property of this sigma field is that the mass is essentially a measure of the inverse correlation length in the QCD critical point. And you know that in such a point, this correlation length goes large, at least in the thermodynamic limit, so that the mass of this particular excitation goes down with some particular critical exponent. And here I show you some examples of different effective models, effective theories of QCD. This is, for example, the quark meson model, and this is the linear sigma model, the O4 model. And the mass of the sigma is indicated in both cases by an arrow. So you see that the mass as a function of the chemical potential in this case and temperature in this case really drops close to the critical point of each of these models. Now, there was some interesting work by Misha Stefanov almost 10 years ago, where he proposed also to look at different cumulants, not just the mass term, so to form different ratios with these cumulants, and again, look at the kurtosis of the fluctuations of the critical mode. In fact, that was one of the motivations, or the main motivation, to look for the kurtosis of net protons. Because as I told you already in the last slide, this sigma is precisely coupled to protons. Yeah? So this kurtosis of a sigma field will translate in kurtosis of net protons. So now what happens when you take the two effects, like this mass dropping of the sigma close to the critical point, and then you combine with the nucleon-nucleon interaction? Well, this can be seen in a very simple model of this one boson exchange, which is the so-called Serot-Walecka model for the nucleon-nucleon interaction, which has, it's a very simple model, has two components, some attractive potential, which is here in blue, which is due to the exchange of the scalar particle, the sigma, and then to describe the small distances, you have the exchange of a vector particle, the omega, which is here in red. So then the first point is that the sigma is the one that controls the attractive part of the potential. And in this model, which has been used to describe infinite nuclear matter, what happens is that there is a large cancellation between the two terms. You observe that these two terms will cancel to give a very shallow potential, not that shallow in this, with these particular parameters, but if more realistic version is something like this. But this is enough to give a stable and bound nuclear matter. Now, of course, you can imagine that if there is an imbalance between these two terms, yeah, so one is not compensated with the other, then the physics will substantially be modified. So now is the question, what happens to this potential when you are close to Tc? And this is what we explored in a couple of papers. And the main idea is that this decrease of the sigma mass near the critical point is not compensated by similar modification of the repulsion. So then your effective potential between two nucleons or two protons will become deeper and will become long range as long as you are closer and closer to the critical point. So then you will get a net attraction between two protons, and this will generate necessarily proton-proton correlations. So here I illustrate this modification of the potential. This is just for illustration. It's not some particular calculation. It's simply using Serot-Walecka potential and then just modify by hand the different parameters of the potential. So here I just change the mass of the sigma by some factor. In any case, this mass cannot really go to 0. So the change is simply a factor of 2 in the mass square, and sometimes also modify the coupling itself, a similar amount. But in any case, you see that the effect is, the supposed effect when you are approaching critical point is something like this. Yeah. In fact, in the final potential that I'm showing here is a factor of the mass, which should be something of the factor of 3, something like this in the mass square. So then we explore what is the implications of this in the dynamics and in the context of heavy ion collisions. Now I should mention here a caveat from a recent result by Edward, where he saw that self-interaction of sigmas, so sigma, I remind you that sigma here also have self-interactions with some couplings. So this might even lead to repulsion of protons when you are very close to the critical point, okay? But only you need to be really close to the critical point. So I will not comment on that anymore, and then focus on this nucleon-nucleon interaction. So then we explored this in some simple model. So we did some classical molecular dynamics of a gas of nucleons interacting through this particular pairwise potential. Now we consider the system in thermal equilibrium, and the conditions were conditions motivated by star measurements of freeze out. So we, in fact, because we are looking at the dynamics of gas of nucleons and not anti-nucleons, So we were looking at conditions happening at low energies, so below the 19.6 GeV of collision energy. So this, more or less this part here, yeah, because we don't have dynamics of antibaryons, as I said. So then, well, we're looking for this molecular dynamics with the average, same average number of protons in some given kinematic cut. Well, we compute the kurtosis, the same kurtosis that it is measured as a function of the potential that we use. So here, the only difference is just we replace the potential between two protons. So here is given in terms of two different kinematic cuts. So if you want to compare somehow with this experimental data by a star, you have to look at the open circles here. But in any case, the point here is not really to compare. I do not dare to compare with experimental data because the model is a simple model. And in fact, I gave here this point as a function of the potential. So you have to read this plot from the right to the left. And the idea is that you are approaching critical point essentially when you go from right to the left. So you have this increase of the kurtosis, which could be a factor of 3 in this range. And if you compare, or you just look at the numbers, you obtain similar numbers as in experiment. Okay, this does not mean that we explain the data, but this means that these results of simple model, although we use similar conditions of a star, have the same numbers as the experiment in this kurtosis, also the increase of the skewness that is not shown here. So that means that the star data might be showing us the effect of this modification of the nucleon-nucleon potential in this region. Okay? So then, if this is the case, what happens if you take this idea one step further? So will you not be able to create correlations between nucleons, but you will also can form preclusters. So these preclusters, what we call in this name, or pre-nuclei if you want, there are strong correlations of nucleons, like collecting a group of nucleons, which are created close to the critical point until freeze out, but in any case at temperatures of 100, 120 MeV. So these are mostly classical states, which are bound simply by this modification of the potential. And these are broad states. I mean, they have not a definite energy. They are broad because the broadening, the width of these states are of the same order of temperature, which is non-negligible. And they should be characterized by some Wigner function in phase space. Now, these are not the same thing as nuclei. Nuclei are the final state particles that you measure in experiment, and you measure at temperatures close to 0. So they don't have this modification of the potential. The potential is now the standard potential. And they are characterized by the wave function. Now the thing is that these preclusters that can form due to the modification of the potential can be eventually decay into ground state of these nuclei. They might simply melt. They might simply decay into say, protons, neutrons. But in any case, well, you can assume that they are formed close to these temperatures. And for example, I show you here some excited states of helium-4. That would be, if you want, like 4 nucleon correlations, yeah, which are excitations of the ground state, helium-4. And you find, this is experimental data in nuclear physics, and then you find many of them, like almost 50 of them with different quantum numbers. Of course, eventually these states will decay into protons, into deuterons, tritons, depending on the decay modes and the branching ratios. So now, with respect to these excited states of helium-4, if you are considering doing statistical thermal models, yeah, and then you want to describe light nuclei, then you need to take into account these states, because at those temperatures, you will also populate every one of these states with the same weight. Of course, as I told you already, they will account for feed-down corrections. And they are not detected in experiment. You measure only the ground state, but you need to take into account in the analysis. Now, the practical implementation was done by Vovchenko and collaborators this year. And they found that these effects of the excited states, not only helium-4, but also other nuclei, like nuclei excitations, is an effect, small effect at high, say high top SPS energies and RIC energies of 5 up to 10%. But as long as you go down in energy, which is the interesting part, the effect could be as large as 60% for GSI or fair energies. So this should be important to take into account this excited state. Even in this case, there's no modification of the potential. There is no critical point going on in this analysis. So my message here is that would be even more important if the potential is modified due to the critical point. You will have even extra production of these states and eventually, well, more light nuclei produced eventually. Now, how to observe this effect when the overall multiplicity of light nuclei is really low in general, right? Because you remember that you need to produce these states at some temperature, and then you have a penalty factor or a Boltzmann suppression factor due to the large mass of these nuclei. Well, the solution here is to look at ratios. If you consider this ratio, this is the number of triton protons over deuterons square, and this was already mentioned in the previous talk by Xiaofeng. So then I should mention maybe already now that this ratio was introduced 3 years ago by this group here in the context of coalescence model, as Xiaofeng explained. Again, in the same context in the same motivation of the critical point, okay? But if you take this, if you consider now this ratio and assume that the statistical thermal model provides a good description, should provide a first order approximation, then you can replace the Boltzmann factor, numerator, denominator, and you will see that everything here that contains energies cancel, mass is cancelled, mass of the nucleon cancel, temperature, chemical potentials, you only end up with a factor, with a number here, pure number, within exactly the same number as in the coalescence model, 0.29. Okay, now you can measure this in the context of the statistical thermal model when you take into account also the feed down of many states, not only also including these excited states of nuclei, and then you observe this result as a function of the collision energy, or you can do the same as in the coalescence model. Yeah, and Xiaofeng also saw a different coalescence model, transport, this is jammed transport code. And then here is a different one, but the result is the same. Essentially, you get in all these approaches, and remember that they do not include any information about critical point or phase transition, you obtain a flat dependence in energy, almost flat dependence, okay? Now, the value that you get, this constant value is very different in the statistical thermal model and in this coalescence model, which is closer to this 0.29. So, well, this is something to be discussed, and in fact, I prepared some slide to discuss about this difference here. So let me not discuss right now and keep it for the discussion session. So, okay, what happens now if you would like to include the effects of the critical point? So then you have to account non-ideal effects on this thermal model expectations, where this ratio just is modified by these factors. Then these factors are simply Boltzmann factors of the potential, nucleon-nucleon potential, which is giving you interaction, so the non-ideal part of the thermodynamics over the temperature. Now, if you allow me to do simplifications, you have 3 powers, 2 powers in the denominator, you get this factor. Overall is this exponential factor of V over T. Now, what happens? If V is negligible with respect to T, okay, you get ideal gas expectations. If this potential is of the same order of the temperature, because you are close to the critical area, then you expect a non-monotonous behavior of this factor. You expect that this factor is 1 away from the critical point, either small energies, large energies. As long as you increase the critical point, this will increase, this factor will increase, perhaps a factor, say a factor E. If this is the same order, potential and temperature are same in order, there is a factor 2, a factor of 2 or 3 enhancement of this ratio, close to the critical point. Then, okay, what happens in experiment? Well, this is experimental data. I don't have much time of discussing every detail here, and let me not discuss low energy and high energy, but just focus on these intermediate energies. So you observe here is data from a star, and also data extracted from NF49 collaboration. And you see this kind of a structure overall, which looks like a peak at some particular energy. In fact, if you compare the top point here at 30 GeV and the smallest point, which is the top Rick energies, 200 GeV, you observe a factor of 2 of difference. Yeah. So then the question is this precisely the effect we are expecting related to the critical point, and then we have a critical point in this area, or is something else? So now a way to test this idea is to consider the helium-4. And why is that? Helium-4 is 4 nucleons, 2 protons, 2 neutrons, and then you have 6 different distances. So you have 6 powers of the interacting potential between each pair of those 4 particles. So now you can construct this ratio that I call O2, which involves helium-4, this alpha particle, and helium-3 in the denominator. And you do the same calculation. You obtain that every temperature chemical potential cancel here. You get a prefactor, which depends on the different spins, the degeneracies of the states, and relations between masses. And also these non-ideal factors. Yeah? This one coming from alpha particle, this one coming from helium-3, where you have 3 particles, so you have 3 potentials. And this one is coming from the deuteron, where you have 2 particles, proton, neutron, and then you have 1 interacting potential. So then overall factor here is the exponential of power of 2 times the nucleon-nucleon potential over temperature. But if you look at this ratio, this that involves is more complicated, but in fact it's not, because with a good approximation, you can simplify this Triton yield in numerator with the helium-3 multiplicity in the denominator. But this ratio gives you another number, and then if you count powers here, this you will get exponential of 3 times potential over temperature. So you will have the effect enhance a larger power than in the Triton yield. So then, okay, what you need to do here is to measure helium-4. But of course, helium-4 is very much suppressed, as you know. You can say that this, you cannot take much data of that because of the huge penalty factor. And in fact, this is true. If you look, for example, at high energies, this is the point here for Alice, yeah? And you see that this helium-4 multiplicity compared to the proton multiplicity is 10 to the power of 7, minus 7. Yeah? This is really much suppressed. But what happens is that as long as you decrease collision energy, this ratio increases, yeah, increases so rapidly. And in fact, when you are at the low energies, and these are experimental data from FOPI, at these low energies, the ratio is not that, it's small, but it's not that small, not negligible anymore. So for the interesting region, where the critical point might be located, then the production of helium-4 is not negligible. And then it should be possible to measure this state. So, okay, so now the point is, of course, there is no, right now, there's no experimental data, at least that I know of, in this intermediate region. So the only thing that I can show you here is an estimate for these ratios, O2 and O3, using the Triton ratio as the experimental values of the Triton ratio as an input. And to do that, what I will use is a technique, a simple technique, which is called the Ffructan solution of the path integral, which is a method that Edward derived in the late 80s, yeah, introduced for quantum mechanics. And here I applied this method to finite temperatures, and also to 2, 3, and 4 particle systems, not just 1 particle in a given potential. Now, this is the case. I don't have time to explain much, but yeah, let me give you some. I have a couple of minutes. Let me explain here what is this. Basically, I consider two particles interacting through this potential here. This is the Walecka potential with some parameters. And then essentially you write down, you go to Euclidean time, and then you construct the action in the Euclidean action for this system of 2 particles. Now you restrict, you separate the center of mass motion to the relative distance, and you solve the path integral in the semi-classical way. So you take the classical solution of this action, and this is at finite temperature. Yeah, and this is what is called the Ffructan solution. Now, the Ffructan solution is used to create a probability distribution like this of the mutual distance of two particles. Yeah? That will give me the probability that two particles are located at some particular distance between each other. Now you can compare this with the classical expectation. The classical expectation is simply the Boltzmann factor of this potential. And I plot here different cases. I mean, these are different temperatures where I compare the classical expectation to this Ffructan case. You observe when the temperature is large, or the potential over temperature is negligible, you obtain good agreement with the classical version. But when the modification of the potential is large, or in this case where the temperature is small, you get differences. Yeah? And these are simply quantum effects. These are quantum effects that are taken into account in this Ffructan solution and not in the classical version. So now the point is the following. I take my experimental data from the Triton ratio, use this Ffructan method to gauge how much is the modification of the potential for each of the points of this ratio. In fact, I have this potential, which is analytic, and then everything depends to the sigma excitation mass. So once I can do this because I have this probability, and the probability allows me to compute spatial averages. And these spatial averages are the thing that I need here. Okay? So then I can do this, and then once I know the modification of my potential, then I go to the new ratios and compute an estimate for these ratios, O2 and O3. And this is the result. In the left panel, this is the ratio O2. And if you focus in this intermediate region, I mean, the trend is similar, the qualitative form is similar as in the Triton ratio, but you observe that the effect is now a factor of 2 more than in comparison to the Triton ratio. So the top point and the lowest point is a factor of 5. If you go now to the third ratio, you obtain this form, again, similar form, but the effect is a factor of 10. So then, with these ratios that involve now helium-4, you enhance the effect a factor of 5 with respect to Triton. And the only assumption here is that the whole effect is due to the modification of the potential close to the critical point. So that would be a test to test precisely this hypothesis. And of course, my message here for experimentalists is that we need measurement of helium-4. Yeah, we have the results for deuteron, Triton, at RIC as well, and NA49 collaboration, but we need also measurements of helium-4. So this brings now to my summary already. And then, well, the main idea is that there might be significant attraction and long-range interaction between two nucleons close to the critical point. And this fact, that would lead to increased correlations between nucleons in general. And in particular, this will affect net proton and proton distribution probability. And this can, of course, be should be seen in cumulant or kurtosis measurements. This can also lead to formation of preclusters or statistical classical correlations of nucleons, which will populate excited states of light nuclei and for example, helium-4, which will later, at the end of the day, they will decay to the ground states or other kind of decay products. And finally, if this is the case, you will have an enhanced production of light nuclei at the critical collision energy. And a way to test this is to do light nuclei ratios. In particular, the one I propose here is the one involving helium, or 2 involving helium-4, to test if there is some kind of peak or not in this ratio at some particular energy. And with this, I finish my talk, and thank you for listening.
Okay, thank you very much for a very interesting talk. We have time just for one short question. I've seen a couple of questions in the chat, but just one question. Okay. Professor Blaszke, please. Go ahead, but short.
Very inspiring talk. I have just one question, which is related to old studies by Rapp, Wambach, and Schuck in the middle of they studied the effect of two-pion exchange between nucleons on the stability of nuclear matter, and they found that, in particular, then this effects on this accumulation of strength in the S-wave channel gives some overestimate of the attraction if one does not take into account constraints from chiral symmetry. And they did that and demonstrated this. So my question is, did you also consider constraints from chiral symmetry in the nucleon-nucleon interaction?
Yeah, thank you, David. I don't really know this word you are mentioning, so I don't know which kind of constraints are
I can
those.
Send it to you. Okay. Mm-hmm.
Okay, I guess probably I don't
later.
think I use that constraints because I don't know.
Maybe later, please.
Okay.
Okay.